Definitely A was on the quiz.
Yeah.
And it does something with sodium.
Filtrate sodium high.
Looks like the Hillis is like where it comes to the point and then you held it. So I guess you could think of the Hillis as like the iliac crest of the ureter. And then the pelvis will like the. It's just regional. They're literally like the same structure. You see what I'm saying? And then look where that's pointing. And then look what this says then.
Yeah.
16. That says it's pelvis. That says it's pelvis. Right here it says pelvis. And then she circled this entire thing for Hillis, so and it'll be cleared up. Because this diagram is different. 16 right here. You're gonna see where that'd be connected.
Okay, is everybody back from break?
I don't know if this is like good.
Can I change the slide, or are you still working on the question?
Does it respond to high level?
Okay. Is that a yes or a no on changing the slide? Okay. All right, so now we're looking at, this is what I covered on the board previously to the activation, what Urine does. So now we're moving to the second step, which is reabsorption. And although this occurs in the distal convoluted tubule as well, most of it's going to occur in the proximal convoluted tubule, all right? So when we look at what's in the proximal convoluted tubule, 80% of sodium ions and chloride ions are reabsorbed. The other 20%, some is going to be excreted in the filtrate, the urine, some's going to be reabsorbed in the distal convoluted tubule, and some's going to be utilized in the nephron loop to make our gradient. And then, as long as the numbers aren't overwhelming, 100% of amino acids and 100% of glucose is going to be reabsorbed. Okay? Remember what the urea was that we talked about? That was a form of nitrogenous waste. We don't get rid of all of it, all right? I don't have a number for it, but some urea ends up being reabsorbed as well. We don't just leave all of it in the filtrate. So we're gonna put in our next diagram, we're going to look at the proximal convoluted tubule. Somehow I lost blood. There we go. So we're going to have a blood vessel over here. And a proximal convoluted tubule here. Cell, anyway. And although it has much longer microvilli than this, I'm not drawing it in there. So proximal convoluted tubule. So this is a proximal convoluted tubule, simple cuboidal cell. What capillary would that be over there? What capillaries do we have wrapped around the proximal convoluted tubule? Capillaries. Peritubular, yeah. That's what it means. It's wrapped around our proximal convoluted tubule and distal, but we're looking at proximal right here. So this would be a peritubular capillary, all right? Which means then that over here we have filtrate. Yellow doesn't show up very well on the board, so we're gonna have green filtrate, all right? So may I erase what I have in blue there? Just because it's interfering with my image of what this should look like. Okay, what did I do with mine? So the stuff that we're reabsorbing came because of the filtrate. So it's in here because it was pushed through the fenestra and the basement membrane and between the pedicels through the filtration slits. So if you had me for Bio 430 in the spring, we covered this already with a process known as secondary active transport, all right? So sodium ions are in their highest concentration inside the cell or outside the cell? Outside the cell. They're the most prominent extracellular ion. All right, so we're going to have numerous sodium ions in our filtrate as well as in the blood, and fewer inside the cell, right? So that means that if we have a channel that is open, sodium ions will move into the cell by just plain simple diffusion, all right? But with secondary active transport, we want to increase the rate at which that occurs. Make it faster than our normal simple diffusion. And by so doing, we're going to couple the sodium movement to glucose and to amino acids. So the diagram we're going to illustrate, I'm going to use glucose. So a secondary active transport require ATP for the secondary active transport to occur? No. That cell process won't occur without ATP, but the active transport, secondary active transport itself is passive. All right, so where do we use the ATP? Down here in the basolateral membrane of our simple cuboidal cell. And this is a sodium ATPase pump, sodium potassium. So it's going to require ATP, which is actually provided on the inside of the cell, to be accurate. And which way are we going to move sodium? Inside the cell or outside the cell?
Inside the cell.
We're going from a low concentration to a high concentration. That's why it requires ATP. And then we're going to pump potassium up its gradient from outside the cell to inside the cell, okay? Now the potassium turns around and just leaks right back out. We're not gonna worry about that anymore. So, is this an antiport or a symport event? Anti, because what? We have the two ions going in opposite directions. So by pumping out sodium, what have we done, or what are we doing to the number of sodium ions inside the cell? We're decreasing them, and we're making the difference in the gradient from outside to the inside the cell even steeper. All right, so sodium's going to move in more rapidly. So that brings us to another transport molecule. And sodium ions do not need ATP. They're gonna move into the cell even more rapidly now because we've lowered the gradient. And glucose, which is sodium won't move into the cell without a protein channel because of its ion charge. Glucose won't move into the cell because of its size. So it needs a helper anyway. So this green channel is both an ion channel for sodium and a facilitator for glucose. But the drive comes from the gradient of sodium. And so it pulls, as it's moving down its gradient, it pulls into the cell glucose or amino acids. Symport or antiport? Symport. All right. So sodium's moving down its gradient, dragging with it glucose. And then it gets pumped out by the sodium potassium pump, and glucose moves out via facilitated diffusion. So back to our macula densa, if this is flowing very slowly, lots of sodium can move across the secondary active transport symport and into the blood and decreases the amount of sodium we have, all right? So let's show this to you. I didn't put the diagram up at first because it's a little scary with all the numbers and lines and everything else, but this is essentially what I drew on the board. Microvilli, those very tall microvilli that we have in the proximal convoluted tubule, function by increasing what? Surface area. So we have lots and lots and lots of room for symport channels. Okay? Now, what organelle do you think we're going to have down here? Mitochondria. Because that's where we use the ATP, is at the bottom of the cell. All right? Good. So we have lots of mitochondria down here. To provide the ATP needed for the active transport at the bottom. All right? Now, it shows here that water is just moving by diffusion across the cell. In actuality, and it's true, but it doesn't just move through the membrane because water is polar and the membrane is nonpolar, being lipid. All right? So we actually have water channels. Remember the aquaporin I talked about? We actually have aquaporin molecules for water on both the surface and the bottom of these cells. So here you can see that not just glucose, but amino acids and some other particles, but these are the two we're going to pay attention to. By the way, when we get to the digestive system, this is the same way that we move amino acids and simple sugars from the intestinal lumen across into the body. Same exact mechanism. Okay? So that's reabsorption. And notice I didn't add any chemicals, I didn't add any hormones, no neurotransmitters. This is just affected by the number of molecules. So if there's a lot of sodium moves across. If there's a lot of glucose moves across. However, we are limited by the number of transport molecules. All right, so if someone is type 1 or type 2 diabetic, they may have too much glucose to move all of that glucose across by the time the filtrate leaves the proximal convoluted tubule. And we don't have glucose transporters other places in the nephron. So if that's the case, glucose gets left in the proximal convoluted tubule, gets left in the filtrate. And glucose is an osmotic, we talked about it on strawberries. So if glucose doesn't get completely moved out of the filtrate, it has an osmotic effect of keeping water in the filtrate. And that's why that's a symptom of type 1 or type 2 diabetes, is increased urine output. Okay? And that's why those people are thirsty, because of the increased urine output and the loss of fluid. So just a kind of a little animation of the sodium getting pumped out and there's more sodium and glucose coming in. Okay? So the terms that I wrote on the board, I want you to understand what and where antiport occurs and what and where, we don't need this anymore, what and where symport and secondary active transport is occurring. Okay? So let me draw, before you take your pictures, let me draw an arrow of illustration. Going from filtrate to blood is reabsorption. Okay? Going from blood to filtrate is secretion. So we do secretion in the proximal, across the proximal convoluted tubule. We're going to be talking about that Wednesday night. Tomorrow night, the Tuesday, Thursday group, when we talk about pH regulation, moving hydrogen and bicarbonate, okay? But in addition to that, in the proximal convoluted tubule, we'll secrete those antibiotic products. So part of the reason if you're on antibiotics, you have to take it every 4 hours or every 6 hours or every 12 hours is because it gets broken down by the liver, and then we we filter, and then we secrete even more. So we move from the blood to here, okay? So the peritubular blood is going to have even fewer of those byproducts than the filtered blood in the efferent arterial, because we're going to add to the solution. Now this is showing some amino acids being added, but primarily for forming ammonium ion, which is a way of buffering. So I'm going to come back, I'm not going to diagram this picture right now. I'm going to come back to it when we talk about acid-base because of our buffers, but I just want to illustrate what secretion is. Okay? All right. So now we're going to look at the purpose of the nephron loop. The nephron loops in the cortex are not very significant. It's the juxtamedullary nephron loops that extend down to in the medulla. All right? So you'll notice before I change diagrams here that we have these numbers 300, 400, 600, 900, 1200. This refers to osmolality. This is the number of particles in the fluid, the extracellular fluid around the proximal convoluted tubules and around the nephron loops. Notice how it's getting more and more concentrated as we move into the papillary area of the pyramid. So the purpose of the nephron loop is to create this gradient. We use primarily sodium chloride ions, but also some urea gets moved out. And it gets moved out in such a way that the gradient increases as we move to the tip of the medulla. The nephron loop, and I can't say this enough, the nephron loop does not concentrate the filtrate. All right? It sets up the gradient, it forms a concentrated gradient around the nephron loop, so that when the collecting duct carries the filtrate back into, so here's the filtrate coming out the distal tubule after creating that osmotic concentration in the extracellular fluid. When it starts to come back down, that's what ADH does. All right, so let me explain that. May I erase the board? So 300 milliosmoles is our standard osmotic concentration of particles, whether we're talking about the blood or we're talking about extracellular fluid, all right? It's equal. So this is the descending limb of our nephron loop, and this is the ascending limb, all right? So this will become the straight, but I'm going to draw a distal because I want to draw it connected to our collecting duct. So our glomerular filtrate in the proximal convoluted tubule has an osmotic concentration of 300 milliosmoles. Right? In the surrounding fluid of the cortex, it's 300 milliosmoles. After it comes back up the nephron loop from juxtamedullary nephrons, it's 100 milliosmoles. Obviously, the nephron loop did not concentrate the filtrate because it's more dilute than when it started. So there's no way the nephron could have concentrated it. All right? But what we'll see is that in the medulla, the osmotic concentration, it's been foreshortened here, goes from 1200. It can go as high as 1400, but most textbooks leave it at 1200. All right, so the gradient has been getting more and more concentrated. And we'll talk about how in just a few moments. But these particles came from the filtrate, which is why the filtrate is less concentrated, because we took particles out of it to make the extracellular fluid more concentrated. All right? So now as our filtrate starts to go down the collecting duct, it's 100. It doesn't get more dilute than that. All right? So if you drank 20 glasses of water today, you probably had to go to the bathroom during a break, and you probably could barely tell that you had peed into the toilet bowl. Probably about the same color. All right? Very light colored, pale, 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 pale. Maybe you haven't gone to the bathroom since yesterday morning, or you went to the bathroom last night, but you haven't drunk hardly anything today, and then it's going to be very dark. So you have removed fluid from the filtrate and reabsorbed it into your body, and your urine that was 100 when it came out of the nephron loop, even late today, by the time it exited into the minor calyx, was probably 1200 or 1400. How did that happen? Antidiuretic hormone causes water channels to be inserted into the simple columnar cells of the collecting duct in the medulla. So as it moves down here, and it's 100, and there's no water channels, it's going to stay 100 all the way down. But if there's water channels here, remember this is 300, and this is 100. So what's the effect of piling sugar onto strawberries? The water moves from the strawberry cell across the membrane into the sugar. Surrounding this with salty water is going to cause water to move out of the collecting duct, and that's going to make this equilibrate. It's not going to get more concentrated. It's going to be anywhere between 100 and 300. So now it moves down here, where it's 600 milliosmoles outside. Again, depending on how many water channels there are, if there's a lot, it'll completely equilibrate. If there's not a lot, it might go to 450 because of the water that moves out. So the whole purpose of our nephron loop is to set up this gradient. That's maintained. And then, depending on whether or not your body needs more or less water, ADH is released or not released to adjust the number of water channels. That's a lot faster than trying to redo the gradient every time you need to keep or release water. Okay? So let's see how that nephron loop works. Couple of things to remember. In the ascending limb of the nephron loop, this is impermeable to water. All right? The descending limb of the nephron loop is permeable to water. The ascending limb has active transport pumps that at the maximum can maintain a 200 milliosmol difference. In other words, there can never be more than 200 milliosmol difference between what's in here and what's out here. Notice 100, what's out here? 300, okay? So if out here is 1200, what's gonna be in here? Nothing lower than 1000, okay? So a couple of key points to keep in mind how this works. Now this whole system is called a counter current multiplier. Remember when we talked about heat counter current flow in the testicular, the tympanoform plexus? So we had a vein that was carrying cooler blood from the testes, flowing by an artery that was carrying hotter blood from the pelvis. And there was a counter current flow. So that even as the artery lost heat to the venous blood and got cooler, it still passed by even colder venous blood, so there was still heat exchange. So we have that with our counter current flow, but it's a multiplier because what was here ends up over here. So that allows us to magnify the effect from 300 here to 1200. Without the multiplier effect, we would be limited to 450 and 350 and 550. Okay, so let's look at this flow here. And so to start this, we've allowed our nephron loop to just fill up with normal filtrate coming from the proximal convoluted tubule. Everything, including the extracellular fluid, it's not just in the middle, it's all around. So it's going to be the 300 out here and the 300 over here. So everything has a milliosmol concentration of 300 milliosmoles. Okay? Now we're going to turn on the pump. And the pump is in the ascending limb. So we pump sodium, and chloride follows passively. We pump sodium out, and some urea also goes out, but we're just going to focus on the sodium. So this is going to be higher, and this is going to be lower, all right? To a maximum of 200 milliosmol difference. Everybody with me on that? So the pumps are in the ascending limb. Now remember I said that was impermeable to water. What would happen if it was permeable to water? The water would leave with it. And we'd still have 300. We'd just lose volume. So if we're pumping out sodium and water could move, both of these would stay 300. We'd just lose volume. But because water can't leave, this becomes more particle rich and this becomes less particle rich. All right? Now, remember I said water can leave this side? So this is higher than this. So now water is going to get pulled out to this one. Notice we're making this more concentrated while this gets more dilute. So we just go up the stream, maximum of 200 milliosmol difference. Countercurrent though, so we're going to allow this filtrate to flow through and we're going to bring some of this over to that side. This is how we create the gradient. Because if we couldn't, if this was not a multiplier, we'd left be 200, 400. And that's the maximum we could concentrate our filtrate was 400. All right, so we're going to put some through. And now we're starting to see a gradient here, but this is still 400. So we turn on our pump again. Difference of 200 milliosmoles. Notice how this equilibrates to that because water is being pulled out by the higher particle concentration. So, getting more dilute, remember that's why I said happens in the ascending limb, but getting more concentrated with the highest concentration at the bottom. So now we allow that to go through again. Almost to 100, okay? But notice, higher, but eventually lower than what it was when it came in at 300. Still 300 up here. But notice still only a 200 milliosmol difference. So by doing the multiplying, by allowing it to come down this side and get more concentrated and then go up that side, we create that multiplier effect. So if I were to tell you that the ascending limb was 225, and I were to ask you what the descending limb would be, 425. It's going to be a higher concentration. It's going to be the same as the intercellular fluid. Okay? All right, so if we finish that, then we get to 1200, which is 200 milliosmoles less than this, 100, which is 200 milliosmoles less, and now the maximum we can do is 1200 to 1400. Kangaroo rats can get up to about 4,000. Guess what? We could never do that unless we had longer nephron loops. So kangaroo rats have much longer nephron loops than we humans do. And so they can create a higher osmotic gradient. Okay? So, descending limb, permeable to water. Ascending limb, impermeable, but possesses the active transport pumps. Okay? This has aquaporins. This is about the only place in the nephron or kidney collecting ducts that does not have aquaporins. Okay? I showed you where the proximal convoluted tubule does, the distal does, the collecting duct, depending on ADH, may or may not, but it can have aquaporins. All right? Okay. Now next, in the Tuesday, Thursday section, I talked a little bit about the characteristics of urine. With you guys, I want to go a little bit farther so we're not here for 3 hours on Wednesday night. Okay? We're just going to do the acid-base balance and not, so I want to go a little bit farther with you guys than I did with the Tuesday, Thursday. My mouse is starting to have issues here all of a sudden.
This isn't that bad. It was the previous one. That's true. For me,
Oh, yeah.
the Renin thing and all that.
Oh, yeah.
I kind of lost track.
So this is just a summary of what we have covered already. So I want to start by talking about the distal tubule, okay? Distal tubule and collecting ducts. So we're not going to worry about inner medulla and outer medulla. That's a little bit more detail that we're going to get into. But here's our proximal convoluted tubule, descending limb, ascending limb, which reminds me of a question. There's something that you guys should have raised a question and said, this doesn't make any sense. I know it's late in the evening, but I said a few things, all of which should have brought you to a conclusion, two at least, that don't make any sense. Here and here, specifically this.
Yeah, the 300 to 600
Nope,
Makes
not that.
No.
But if you had a question.
Yeah, I was like, if the difference should only be 200, then.
No, this is osmosis. This is
Okay.
not a pump. So this is the salty concentration pulling fluid out until it equilibrates. But that leads me to the question you should be asking. If we're pulling water out of this, or we're pulling water out of this should not stay 300, 400, 600, 800, should it? It should become dilute, because we're pulling water constantly into that. Well, we've already talked about the structure that saves the day for us, and what is it? Another countercurrent, not a multiplier, but another countercurrent structure. I put my model away. Remember the vasa recta? The vasa recta flow countercurrent to each other and countercurrent to the nephron loop. So when the nephron loop is flowing down, the vasa recta are flowing up right beside it, and the vasa recta are flowing countercurrent to each other. And essentially, they function to carry away the fluid removed in creating the gradient, and they carry away the fluid removed from the collecting duct during the concentration. Otherwise, we just dilute everything and it would stop. So we need to transport that fluid out of the area in order to allow that osmotic gradient to remain. Otherwise, it'd be completely diluted by the fluid being pulled into it. Equilibration would occur. Okay? So we're going to look at two regions, and this is very simplified. The distal convoluted tubule and the collecting duct in the medulla. Okay? So, let's go back here to aldosterone. In the distal convoluted tubule, we do continue to remove sodium. Again, not all of it, because there's still sodium in the filtrate when it's excreted. But if your body, for blood pressure reasons, needs more fluid volume, and aldosterone is released. Is aldosterone a amino acid protein hormone or a steroid hormone? Steroid. So it's going to pass through the plasma membrane. Its receptors are inside the cells of the distal convoluted tubule, and they're going to affect. So here it's coming in. Here's the filtrate over here. It's coming in from the blood, binds to its receptor inside the cell, and causes the nucleus to make more sodium channels and more sodium potassium pumps. And that results in more sodium being removed from the filtrate in the distal convoluted tubule. To some degree, the collecting ducts up in the cortex, all right? But I'm going to focus primarily on the distal convoluted tubule. So aldosterone increases sodium reabsorption. And it does so by changing the nucleus of these cells and increasing the sodium channels, which are going to remove sodium. When sodium leaves the cells, what happens to water? Chloride follows passively too, but water goes with it because it's an osmotic. So when we have aldosterone, we decrease urine volume, and it becomes more concentrated, all right? And we increase blood volume. Do we change the osmolality